So let's start. So what are genetic algorithms? Basically, these are some. This is the algorithm that is inspired from the biological evolution, and whatever is happening like in biological evolution, that is mimicry. That is, we have simulated the same kind. We try to simulate the same things in kind of programming or in kind of in steps to simulate those things, and we have found that if we use the same process, we can optimize our function. Um, we can find out the minimum or maximum using genetic algorithm in the very simple sense. So let's see, and for I will take two examples, working examples, for to understand this genetic algorithm. I feel that while going through a lecture through example, we will have like better understanding of genetic algorithm rather than going to through the symbolic representations. So learning method is motivated by analogy of biological evolution rather than search from general to specific or from simple to complex. Genetic algorithms generate successor hypothesis by repeatedly mutating and recombining part of best current known as hypothesis. So, as in general, what we do, we start from like some hypothesis, and we at every step we try to refine our hypothesis towards the direction of a solution, and step by step we will finally optimize our objective function. In general, what we do that, but in genetic algorithm, we take several hypotheses at a time, and we see how these hypotheses are performing. Those hypotheses which are performing good in comparison to other hypotheses, we focus generally on those hypotheses only. At each step, a collection of hypotheses called the current population is updated by replacing some fraction of offspring of the most fit current hypothesis. So in general, what we do, we start with some guesses, random guesses that it could be the solution of a problem. Let's say I have to find out a solution of a problem, and I will start with some random guesses that this could be a solution, that could be a solution. For example, I come up with 10 different random solutions. I see how these random solutions are behaving in respect to my problem. Those who are perform and these 10 random solutions, I will say this is my first generation, and I will evaluate these 10 solutions on my problem, and if I find out that 5 are performing okay and 5 are performing worst. So I will do some steps, or I will adopt some methods, so that I will proceed into the direction where I will find good solutions, whatever in comparison to whatever I am having right now. So genetic algorithm problem. Search a space of candidate hypothesis. Candidate hypothesis means I will take several hypotheses at a time. So candidate hypothesis is that hypothesis which I am currently using to evaluate my problem. So I will take search a space of candidate hypothesis to identify the best hypothesis. So I will take at a time, as I already told you that may be possible that, for example, I take 10 hypotheses at a time, and my problem is to find out which is the best hypothesis, not among those 10. But during the process, I will finally end up with the best optimal hypothesis that could be there. We will see in example, just for the sake of a theory, and to get a familiarity, I will just introduce few terms, and then we will switch over to the numerical example. The best hypothesis is defined as one that optimizes a predefined numerical measure. What numerical measure is, like for an example, we had error function in that curve fitting case. So here also we have some numerical measures, so to evaluate how my hypothesis is doing. So this is called a fitness function. So basic structure of genetic algorithm is iteratively update a pool of hypotheses. So we have pool of hypothesis means first generation we come randomly, we take some few solution or few hypotheses and assume that they may do good on our problem. So iteratively we refine or we change those hypotheses using some operators that we use in genetic algorithm, and gradually we will find out that whatever we started with some random hypothesis and end up with a final hypothesis that is optimized one. So basic philosophy, here I will introduce some terminology. So a solution generated by genetic algorithm is known as chromosome. So generally what we do, we represent our hypothesis in terms of chromosome. For an example, my hypothesis is, let's say this is my hypothesis. Let's say AX plus B is my hypothesis. And what I am doing, because what I am doing, this is my variable A and this is my variable B. Let's say I am representing my A with 4 bits 0001 and B also with 4 bits 0100. So what I am doing here, I am saying that X plus 4 is my first hypothesis. I can code this thing into a string form. So here this one is represented by these 4 bits and this 4 is represented by these 4 bits. Now let's say I take second hypothesis. Let's say this is 3x plus 4 plus 5. So my in the second chromosome will be 0011, for that represent 3, and 5 is 0101 that represent this thing. So likewise, I can represent my hypothesis in string forms, and these are known as chromosomes. So for an example, I started with 4 different hypotheses in the initial step. Those 4 hypotheses will be this. Let's say this is my first hypothesis, this is my second hypothesis, and likewise I will take third and fourth. Randomly, I will take any 4 hypotheses, and then these 4 hypotheses will constitute a population. So in my first generation, this is the first generation. My first generation is having 4 chromosomes, and my population of first generation is 4, right? I will do some refinements over it and I will produce my second generation. So there are variations of genetic algorithm. For here I am taking very simple form. So in my second generation also, let's say I am taking again population size 4. So these 4 chromosomes again generated, but they could be quite different from the previous chromosomes, previous generation chromosomes. So this is my first generation, this is my second generation, and likewise I will generate my third generation, and these third generation will also constitute some chromosomes, and chromosomes will represent some hypothesis. Right. So the first point, a solution generated by genetic algorithm is called a chromosome, while collection of chromosome is referred as a population. A chromosome is composed from genes, and its value can be either numerical, binary, symbol, or character. So here, for an example, my chromosome is having these values. So it have 8 genes, 001, 0100. So my chromosome have here 8 genes. So for an example, this is a binary representation. If I want to represent my chromosome, for example, some numerically, I could say that my I have 3 and 5. So this is a numerical representation in chromosome. So I can represent my hypothesis with either numerically, binarily, or symbolically, or in character form also. So these chromosomes are constituted by genes, and these genes have some value. It could be 01, it could be number, it could be symbol, or it could be character. These chromosomes will go under a process called fitness function to measure the suitability of the solution generated by GA. What is this? Sorry to interrupt you. Since we say chromosome is a solution, does that solution mean a function that can satisfy a specific training set? Population mean a group of such chromosomes that all of them satisfy the same training set. So I will take an example just to give you a very good clarity. Right now, you just with the terminology. So chromosomes, now you got it, that the chromosomes are used to represent a hypothesis, right? So for now, just take it, and we can represent a chromosome with the help of genes. So there are a number of genes, and genes could have a different type of numeric binary symbols. To evaluate a chromosome, we will use some fitness function to see that how my hypothesis is doing. So, for example, I have hypothesis. So that how my hypothesis is doing, we to evaluate that hypothesis, we use fitness function. Some chromosomes in population will mate through. So once I find out that there's some hypotheses are good and some hypotheses are bad using fitness function, those hypotheses that are good, I will take them and go and and process them through a process known as crossover. Crossover is similar as you read in biology, that male chromosome crossover with the female chromosome, and they take some part of our parents, like partial parts from both parents, and constitute a new chromosome. So that's how it goes under a crossover process, and it gives, and that new chromosome that formed from a crossover is known as offspring. In a generation, a few chromosomes will also mutate. Mutate means, for an example, abrupt change in something. For an example, I have something like this, and this is my chromosome, and it goes under mutation. So it may be possible that that without any reason the value gets changed. For example, this bit gets changed to 1, and all the remaining bits are same. So mutation generally they have, as you, for an example, mutants or mutation generally happens when there is some kind of a abrupt change in a chromosome, and it will result in a different kind of a living being. So chromosome is again a chromosome generally, or terminologically, it means that there is some abrupt change in a chromosome without any reason. So that is mutation. So crossover and mutation is controlled by crossover rate. So I don't want to go into that to how it happened in biology or so. I will just come to directly to the part how we implement it. So there are two, crossover rate is there, like how frequent is there that we will, our hypothesis will go under crossover, and mutation, how frequent our bits get converted or flipped using mutation. So it is very rare to have a mutation, but yeah, there is some rate that we have to mutate. So there is some rate that we will find out how to do mutation, like if the bits will be flipped around, or how many it will get changed due to mutation. So generally the rate is less for mutation, and crossover is okay. GA means algorithm. So the next generation is generated through Darwin's evaluation. After several generation, chromosome will get converted to the solution of a problem. There are some steps. So in first step, we determine number of chromosomes. Like we represent our hypothesis using chromosomes. So we will first find out how many hypotheses we are going to take. Let's say we say at the beginning we will take 10 different hypotheses. It means it will take, then we have to take 10 chromosomes that represent those different 10 hypotheses. Darwinian evolution rule is like, if you remember your ninth class, there was a Darwin theory, like survival of the fittest. If you remember, I don't know. So survival of the fittest says that who will change according to the needs will only survive. For an example, uh, giraffe resultant of a Darwin evolution. Darwin hypothesized that this is because the organisms that have to survive, they have to go like this theory, survival of the fittest. That is Darwin evolution rule. So in here in this algorithm, it means those hypotheses which do good will survive only, and those hypotheses which don't do good will die eventually. That is known as Darwinian evolution rule. It is a kind of an intuition that you can take in Darwin evolution rule here in this genetic algorithm, right? So, for example, at first determine the number of chromosomes generation and mutation rate. Find out how many chromosomes you want to take out at the first generation, and like what is the mutation rate that you want to consider. These are the parameters that you think before implementation. Mutation rate means how high frequent you want to mutate your chromosome, and what is the crossover rate value. How, what do you want, like is do every chromosome has to go through under crossover process, or there are some, or you want some uh, chromosomes to go directly proceed to the next generation and some partial chromosomes go through a crossover rate. So this is all need to be taken care of before implementation, and for everything you need to find out what percentage you want to do that. For example, mutation rate is very low, for example 0.001. You want that out of 100 bits only one should mutate, or it should change its value. Crossover rate means, for example, at first you take 10 hypotheses in your first generation, and you want only 5 or half of your chromosomes to go through a crossover rate, to go through crossover process. So it means your crossover rate is 50%. So these are the parameters that need to be fixed before implementation. Generate chromosomes of the population, and then and the initialize the value of genes with a random value. So randomly you take any chromosomes at first, then evaluate those chromosomes using a fitness function, do crossover and mutate and find out the solution of the first generation. So let's take this is a flow chart. Here I am representing. So if we say chromosome is a function, then what is a gene in it? So gene is representing a parameters value. Simple. You can say that gene is somewhere constitute a parameter value. I told you this. For example, you want to represent this hypothesis ax plus b. Now you want to represent a chromosome with the help of this a and b, right? This a could be integer that can take, let a and b integer that could take a value between 1 to 30. Your problem is like that, for example. Now a is a gene and b is a gene. A could have a value between 1 to 30 and b could have a value 1 to 30. So this is what genes are. There are two genes in this chromosome, and each gene can take a value between 1 to 30, right? X is not a gene here. So I told you that you have to represent your hypothesis. So hypothesis is a line, right? And for a line, here in this example, hypothesis is if hypothesis is a line, then it will take only two coefficients. What is the slope of it and what is the intercept of it? So it depends upon a problem. Don't go particularly here in this what I am giving an example. It depends upon how you're representing your hypothesis. Once you fix that you are want to represent your hypothesis like this, that's fine. So solution, you first represent your hypothesis in form of a chromosome. That will constitute a population. You evaluate whatever you have taken randomly. Those who are fit, you will select those fit one and leave the worst one. Those who are performing bad, leave them. Those who are good, do the crossover on it, then mutate. These are the operators that you want to do during the genetic algorithm process. If you have decided that the criteria is met, for example, your objectives you got a minimum or a maximum, whatever your objective was. If that is met, just end it. If that doesn't met, then go to the next generation. That is second generation. Again, generate the population, but this time the generation that you have generated, you don't have to take it generate it randomly. Now the second generation comes from the first generation crossover, right? So let's take an example first. So this is a problem. Can you hear me? Okay. Okay, so my problem is like my objective is to find out the solution of this equation. So I have equation a plus 2b plus 3c plus 4d equals to 30, and now I want to find out what are the values of a, b, c, d, right? So this is the this is the equation. This is the objective of my function. The objective of my problem is to find out the value of these variables a, b, c, d. And let's say I cannot take these values like. So what are the best values that I can take? So how I will represent this thing? I will form this. I just convert this equation into this form, right? And my objective is now to minimize this function, because once my a b c d value satisfies 30, so it means 30 minus 30 equals to 0. So it means I will get 0 only when my a b c d into the equation gives 30. So that is my objective now. So I have to minimize this function fx. So and right. So let's say that a b c d can take only one value greater than or equal to 1. So this is that I have already that I have considered for my problem, that my ABCD can take a value between from 1 to 30. That's obvious, because if you take greater than 30, then obviously I am just considering here positive numbers. So that will not satisfy. So obviously the feasible range of my numbers is between 1 to 30. So my chromosomes that I constitute will be resemble like this. So my chromosome have four gene A, B, C, D, and and each gene could take a value between 1 to 30, right? So randomly I initialize my first generation. So in my first generation I take six chromosomes, 1, 2, 3, 4, 5, 6, up to six chromosomes are there, and randomly for each I have generated these chromosomes. So how I can do that? So for example, there are 34, 20, there are four values and there are six genes. So 6 fours are 24. So I need to generate 24 random values between 1 to 30. I will generate 24 values between 1 to 30, and every first four values will constitute my first chromosome, second four values my second chromosome in an order. Likewise in third, fourth, five, six. So I will generate 24 random values between 1 to 30, and I will form my six chromosomes. That's very pretty simple. Now I need to decide what is my objective function. So because you know that my objective was to minimize this function, right? So my objective was to minimize the function. So this was my objective. So what I will do, I will say that I will convert my I will set my objective function like this. So first I will evaluate a value. Sir, why minimize? Aren't we supposed to make a sum equals to 30? Oh my God. Sir, if you see it carefully, uh, when we do this like a plus b plus c in this equation here, a plus b plus 2c plus 4d, we must get a values equal so such that our sum equals to 30. Now what I will do, I will take this 30 to the left hand side. Now this is like saying that the equation minus 30. If equation goes to equals to 30, obviously 30 minus 30 equals to 0. So this equation only satisfy when this equation equals to 30. Oh my gosh. Okay. So now I will take my this I just feed all these 24 random values here in this my function, right? This is my function a plus 2b plus 3c plus 4d minus 30. One by one I will evaluate all these six chromosomes, how they are doing. So for first chromosome I got 93, second chromosome I get 80, for third chromosome I get 83, my fourth chromosome get 46, 94 and 55. So likewise, I evaluated all those chromosomes and I found out that these are the values. Okay, so far no problem, I think. Now we have to find out our fitness function. So let's say fitness function is, I have decided my fitness function like this: 1 upon 1 plus fx, right? So this is fx, and fx is a plus 2b plus 3c plus 4d minus 30, right? So why I'm doing like this? So for an example, my motive was to make this fx equals to 0. When this fx will get 0, my objective function or fitness function will get 1. So if this is not equal to 0, if this is not equal to 0, then my fitness function will have some value, and it is in denominator. When it is in denominator, then I will get some fractional value. So my objective function that is like best when I will get something, when I will get a value close to 1, and otherwise it will be in a fractions. So this is my fitness function here. So I will just feed my fitness function, and I'm just adding 1 here just to make sure that if fx does get to 0, it will not converge to infinity or undefined thing. So I just add another fitness function, could be 1 upon fx directly, right? And you make sure that fx is not equal to 0. Like you did in SVM, your fitness function was w square, right? 1 upon w square. So here you are taking your fitness function 1 upon fx. So this is fitness function whenever every time you want to minimize it. So to avoid that plus 1 upon 0 undefined condition, I'm just adding 1 to it. 1 plus 1 upon fx. That's it. So this is the absolute value. If you look carefully, this is absolute value I'm calculating. If it is so absolute value means always 0, always positive. So when this number is positive and this is positive, so if this fx gets 0, then my fitness value will be 1. If this fx is not equals to 0, then my fitness value will be always less than 1. That is in fraction part. So my ultimate aim is the fitness is always high for the good hypothesis, and fitness is always low for the bad hypothesis. That how I come up with my fitness function. So depending upon your problem, you can come up with different fitness functions. So first, now you are calculating fitness for each. There is a question here: what is the intuition behind making objective function x tends to 0? What? Are you serious? You should look at very carefully. This is not that easy subject thing. I don't want to repeat it again and again. What is intuition behind making objective function f x tends to 0? The intuition is very simple. This was my equation. I want to satisfy this equation, right? And I'm looking for a b c d value here. This a b c d values, every time it satisfies, it means if a b c d satisfies 30, I will get 30 equals to 30, right? So what I am just making bringing this 30 to the left hand side. Now 30 minus 30 will be 0, right? So if this is what I am calibrating, this is fixed, right? This is fixed. This 30 is fixed here. This is what I am calibrating. So every time I just want to make it 30. So every time it make to 30, it will goes to directly to 0. So I don't know. You should look. You should just look this again, right, Amardeep? So this is how I am calculating my fitness for each chromosome. 1, 2, 3. So now my fitness function. I have calculated my fitness. So right now the thing that you need to be care of is like what is the relative percentage of each chromosome. So how you will be calculating it? For example, this is a fitness from first chromosome, second chromosome, third chromosome. So the total fitness that you are getting is this. Now, if I will find out like this is the total fitness, what is the probability that what is the portion? what is the portion of this overall fitness that is contributed by chromosome 1. So chromosome 1, then you will say that the fitness value is 0.0106 and total fitness is 0.0845. So this is the contribution by chromosome 1 of the whole percentage. So this is the total thing is 0.0845, and this is the contribution by chromosome 1. So the what is the effective percentage given by chromosome 1 is this. Similarly, for chromosome 6, the effective percentage 0.0179 divided by 0.0845, right? So likewise, you will calculate what are the different percentages or probabilities that will be contributed by these chromosomes. So these are the probabilities by chromosome 1. The probability for each chromosome is formulated by this, and this is quite mechanical. You know this. Just to add to your knowledge, I would tell you, so far nobody has done any analysis on genetic algorithms, whether they are converging or not or nothing. But very supernaturally, they are giving us a good result. So these steps are quite mechanical in terms, and there is very less analysis available for these algorithms. So you need to learn like what is the process, what are the steps you need to follow. That's it. So this is the probability that you are calculating like this. Like now, now you want to select it. This is a very important part. You want to select it like so far what you have done is like which is the good one, which is the best one so far among all these things. So you know the total was 0.845, right? The total thing was 0.845. This was the total. And among all, to find out which is the best one, the one who is having the greater numerator will give you the total. The fraction equals will result in a greater value, those who are having a greater numerator. So in a very simple sense, if the chromosomes that are having a good larger fitness value will result in a larger probabilities. So here, for an example, this is the largest value I got so far, right? So this is the largest probability. It means my fitness function, my chromosome 4. What was my chromosome 4? It was giving me this value. So this is the highest thing that I got. And what is the chromosome 4 is giving? If you see here that my chromosome 4 is very near to the optimal solution among all these things. So my optimal solution lie near to 0, right? So which number is near to 0 in among all these numbers? This is chromosome 4 resulting into 46, that is near among all. So that's why my chromosome 4 is having the highest probability because of this. So ultimately I need to, so this is all. So what you so far you have done, you have evaluated your chromosomes according to fitness function and find out what are the probabilities they are having right now. So according to the probability, you want to select it for the next generation. So do we really need to form a fitness function? Can we not work with fx value that we got? So fitness function is to evaluate or to measure your current hypothesis. If you feel that your current fx is okay to, if your current fx is a good measure, then it's fine. You can do it. It's not a problem. So fitness, what you need to take care of is that every time you take a fitness function, it should be a good measure of your hypothesis on the problem. It should measure like how good your hypothesis is doing. That's it. So for an example, if I would have taken here fx as it is, any basis on which we form a fitness function. So that's why I'm giving you example here, sir. So is adding 1 in the denominator like Laplace smoothing you just discussed in the past? No, 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 no. It's not like I'm adding 1 to it so that as smoothing. No, no, it's not at all that thing. So my fitness function is like Uh, my fitness function will be like what I want to measure my fitness, like the bigger the number is. For example, here I am trying to say the bigger the number of fitness is, the better the chromosome will be. If I want to evaluate my fitness like this, that's why I am doing 1 upon fx, because 1 upon 1 fx. If I want to find out, if I let's say I assume that my fitness should be like the lesser the number is, the great good the fitness would be, then I don't need to put it into this form. Then directly I will take fx. The lesser the fitness will be, the good the better the sorry, the lesser the value of fx will be, the better the fitness will be. It will be inversely proportional. But just to simplify it, like it will be directly the greater fitness, the greater the good chromosome will be. That's why I did it into 1 upon fx. If you want to do it inversely proportional, that's not a problem. You directly take fx. So for just forget what, just don't think about, just first understand the steps that are more crucial. So I will take questions one by one after that. First try to understand how I'm implementing this genetic algorithm. So for my first generation, what I did, I evaluated my fitness function and find out the probability of each chromosomes, right? So far I have calculated my chromosome. Now I want to select these chromosomes for the crossover thing, right? My first step was to form a generation, to form a population randomly. I did that. Then I evaluated my chromosomes using fitness function. I did that. I find out which chromosome is having what probability. I did that. Now I want to select, based on these probabilities, I want to select these chromosomes, like which will go for the uh, which will go for crossover. So my idea behind is like those chromosomes which are good, doing good, should go under the crossover process. So these only participate in generating a next generation. So it's intuitively like if father is very strong, mother is strong, very strong, then we want them to mate to get a good offspring. So here the idea is similar. Those chromosomes which are doing very good, according to the probability, we will select them for the next generation to get take them to process them through a crossover process. So how you will take them? That's the important point here. So there is a selection criteria. There are different selection criteria. I am want to discuss here a roulette wheel. So how do we implement roulette wheel? So if you remember what is a roulette wheel, if you go to a casino, you will see that let's say there is a red number here. It takes 50%. This is a blue. Let's say this is a blue color. This is a red color, and this is a green color. So this is 25% area. This is 25% area. This is a 50% area. I want to generate. If I will, this is my pointer here, right? This is 6 here. So if I rotate my wheel, and so there are 50% chances that it will always stop. My red color will always stop in front of this indicator, because it covers 50% of the circumference. But and there are 25% chance that it will stop for blue, and 25% that it will stop for green. So I can see that from the in the probabilistic view, if I want to generate some number according to this wheel, then the number generation or the distribution of number will be, for example, I will generate 10 numbers from here, or 10 colors from this wheel. Then there will be 50% chance that the color will be red, 25% chance there the color will be green, and 25% chance that the color will be blue. For an example, I will take generate 12 numbers, 12 colors. So there will be 10 R, 6 R, right, and 3 blue and 3 green. So because the probability distribution of this roulette wheel is like this. So similarly, how to implement is here in this genetic algorithm, what I do, I take my first probability 1.25, and this is my roulette wheel. This is my starting point, right? So this is my probability 1.254. I just mark this as my chromosome 0.1254. So my second thing will be my second probability is 1.1456, but on the wheel it will go up to the first I will take this term 0.124 plus. So this will go up to, I will add 0.1254 into my second probability chromosome 0.1456. So the total thing will be, I will get 0.2710. So this 0.2170 is from here to here, right? This 0.2170 is from, let me mm, this 0.2170 is from here to here, right? Because this is addition. And this 0.124, this 0.214 is from here to here, only from here to here. Now I have to take my third boundary, and then I will add all these three number, and that I will get 0.4188. So this is, let's say, 0.4118. So it is from here to here, right? So similarly, I will constitute like this, and I will have some numbers. So this is, the next number will be 0.6639. This is 0.6639. The fourth number is 0.7882. This is 0.7882, and finally my, this is where I have started. I will end up here only, and I will get 1, right? So this is my wheel, right? This is how I will form my wheel. So then I just find out what is the cumulative probability distribution. Now to select it, what I will do, for an example, I will generate some random numbers, right? So I will generate some 6 random numbers, and for every random number, let's say I am generating it between 0 to 1. So if my random number is 0.024, if my random number is 0.024, I will see on the wheel where it lies. So what the number was? It was 0.201. So 0.201, where it will go? Oh my god. So it will go somewhere here, 201, right? So it will come somewhere here. So this 201, right? 201. So somewhere it comes into this part. So this belongs to chromosome 2, right? So that's why I choose chromosome 2. Now I generate my second random number, 0.284. I will see where it will fall into the line, 0.284. It will come lie in this section. So it belongs to C3. So that's why I generate chromosome 3. Then I generate 0.099, where it will lie. 0.099 will lie on this part, right? So it will belong to chromosome 1. So I generated chromosome 1 here, right? Then I generate this, my random number is 0.822. 0.822, where it goes? 0.82 somewhere here. So my 0.822 will go somewhere here. Oh my god. So this is somewhere here, 0.882. So this belongs to chromosome 6. So that's why I got chromosome 6 here. Now 0.398. So 0.398, where it goes? 0.398, 0.39. It will goes again to C3. 0.398, right? So this is 0.398 goes to chromosome 3. That's why chromosome. Then finally 0.501. So 0.501 will be somewhere here. This is chromosome 1, 2, 3, 4. This is chromosome 4. So that's why I generated chromosome 4 here. What is the criteria to generate this random number, or simply just I will tell you. That's a good question, but at the end of this lecture I will tell you how to generate these random numbers. So that's a good question here. So for an example, for time being, just think that whatever comes into your mind. Say I generated chromosome 4 means what? So it means that now what you have done here, yeah, that's also a good question. So what you have done here so far, that you have calculated what is the probability to what probability belongs to which chromosome, right? Now you want to select your those chromosomes only which should participate in the crossover process. So it means you want to select those chromosomes. So you want to select your chromosomes means now you have a pool of 6 chromosomes. Now you have a pool of 6 chromosomes, and this is a probability distribution. This is the probability distribution. So out of these pool of chromosomes, with this probability distribution, you are selecting again 6 numbers, but these 6 numbers could be different from the previous number, right? So just to show you here, for an example, this was my previous generation: chromosome 1, chromosome 2, chromosome 3, chromosome 4, chromosome 5, chromosome 6. So these were the 6 chromosomes. I evaluated my fitness thing, I evaluated the probability, I turned the roulette wheel, and according to the roulette wheel, I generated again 6 chromosomes. But I generated 6 chromosomes according to the fitness of these chromosomes. Now here you see that my 5 has not appeared into this criteria. So here 3 appeared twice. So 3 appeared twice, but 5 has not appeared here. So it may be possible that those who are having the largest probability will, will reoccur again and again in the crossover process. So meaning you generate 4 random numbers. No. These are the same chromosomes. These are the same chromosomes. For example, I am saying that I generated chromosome 2 here. So this is a 2 chromosome, right? Second chromosome. See it. 0.22118.3. 22118.3. Right? When I say I generated chromosome 3 according to my distribution. So this is 10, 4, 13, 14. So this is 10, 4, 13, 14. Right? Do you understand this? Okay. But 4 was the best before. So this is the probability distribution. You're right. The 4 was the best before. But I'm not guaranteeing that if my 4 is best, I will certainly take it. That is the probability, sir. I need to generate it according to the probability distribution. It is not always that 99% you are sure that you will always be correct. That is probability. You need to understand what is probability. If somebody comes and asks you that there is a 99% probability that India will win, it doesn't mean that India will win. It may lose also, because there is a 1% probability there. That you should be very careful while taking consideration of this probability thing. Okay, so I hope that this would be clear now. So this is just a beginning. So now what I have done, I have find out what are the chromosomes that will going to participate in like crossover thing. So for an example, I have selected my chromosomes. So first I had my random chromosomes. I generated my chromosomes again according to like their fitness things or their fitness distribution. Now I have 6 chromosomes again. Now these are my current chromosomes that I need to focus on. I just forget those random things now, because you have selected according to the fitness thing. Now you have selected 6 chromosomes here again. So in that, so somebody is asking, can you go to the previous slide? Yeah, I am here, sir. What do you want to know? And tell us, what did we conclude? We didn't conclude here. We are just selecting the chromosomes. We are just selecting the chromosomes. In this process, we find out according to the distribution we selected our, we had these 6 chromosomes at first, that randomly, right? Now according to some the mathematics and probability distribution, we selected some chromosomes by some process, and we got these chromosomes here. In this process, we lost chromosome 5. So what do you mean by new chromosome 1 equals to new chromosome 2? It means, so new chromosome 1 means now in selection process, now you want to select your first chromosome. So you need to select, right? You need to select according to the distribution. You are selecting your first chromosome. You are selecting your second chromosome. So it means here that I am saying that when I am selecting my first chromosome, that my first chromosome according to the distribution is the second chromosome which was previous there. Because I am rotating my roulette wheel, right? So roulette wheel always stops somewhere in on the chromosome thing. So this was my roulette wheel. It will always stop on the area among these 6 chromosomes that was there before at random. So out of these 6 only I have to take according to the distribution. So out of these 6 chromosomes, I turn my roulette wheel, and that roulette wheel stops in front of the second chromosome area. So at first selection, I select my second chromosome. So it is like when I rotated my roulette wheel, and this is my indicator. This is my indicator. So it stops, this roulette wheel when it stops, that second chromosome area will be in front of it. Right? When I rotate this roulette wheel again, my third chromosome area will be in front of the indicator. So likewise, I will rotate my roulette wheel 6 times. Every time it stops in front of some indicator, I will choose that chromosome. How to do it in computer? That's why we calculated this cumulative cumulative distribution thing. Okay. So are we re-baselining our chromosomes? I don't understand what do you mean by re-baselining. Can you simplify it? And this exercise, we lost chromosome 5. What is re-baselining you mean to say? We are selecting it, right? We are selecting it for the chromosome, for the crossover process. We are selecting it for a crossover process, and we are selecting according to the fitness thing. So in this process, we lost chromosome 5, right? Okay, sir. Just a short break because my throat is having little trouble now. I will continue just after 5 minutes. Don't go away anywhere.